years, let us apply these common sense rules on the internet. So this is the analogy of what we do today, the castle. And this has happened also in real life. I mean, people build castles, and unfortunately, always those castles were, sooner or later taken over by the adversary. So other things which could be problematic in today's internet is that authentication is done only at the destination. As I said, the castle model depends on the node, destination node. And all the resources in between are left to be used by attackers if they want. Okay? So basically this type of defense, we believe that it's very unscalable. And to show with a figure that, this is what we are dealing with. So here is our network, our node, our computer, our castle, facing potentially the whole internet. So anybody could be our adversary here. And nobody is stopping them. So the only defense we have is here. So that's why I call it unscalable. Because here you are facing millions of potential problems. And of course, sooner or later this castle will fall. There is no way it can stand this type of attack. So, and the history of castles and buildings has long history. I'm mentioning just this Maginot Line, which was built by France and couldn't stand the attack from Germany. It was taken over in a couple of days, even though it was very, very good from a security point of view. But again, it's not a question how strong the castle is. It's the model itself which cannot stand attacks. Another problem with security is that this castle problem. So let us compare with real life, because I said that let us take some lessons from real life. In real life, our houses are not castles. We don't have this kind of protection in our houses, right? Anybody can break them. Okay, we don't have guns ready to fire anybody, and the reason because we have society, we have laws, okay, and bad guys are not stupid. They know that if they would do something, they will be, persecuted and most likely end up in jail. So that's the power of punishment. Now, why this doesn't happen in internet? Because in internet, most of the times you are not even able to follow who is, and to understand who is the attacker and to persecute. Okay, so basically we should like to build something which is close to real life and implements the same power of punishment or prevention of the punishment. Now, why architecture comes in the picture? Because, as I said, we are dealing with patches, and a lot of patches might be the signal that the problem is more fundamental. And to show you that just simple architectural decisions have big effects in security, let us consider just the IP address, or why the telephone networks are much more secure than the internet. One reason is that you cannot change your telephone number. Okay, it's assigned to you, and if you do bad things from your telephone number, your service provider would know, and anybody potentially could know and persecute you and make you accountable about that. On the internet, anybody can fake IP address. We get a lot of junk, and we can do nothing, because if you follow, most of those IP addresses are fake. Because the IP address is soft. It was designed at the beginning to be soft, changeable, and you see this decision has opened the door of a lot of consequences. Okay, so basically that's the power of architecture. A small decision there has big consequences. So basically the same thing now could work in fixing problems. So we make better decisions at the architecture level, which can provide much stronger security. So the same thing with firewalls. Firewalls again are per hop behavior. So basically they guarantee just at that point what happens, but they don't guarantee anything about security end to end. What happens behind the firewall or before the firewall, nobody knows. So there are several alternatives. So one very extreme, which I mentioned here, this negative availability. Basically, in today's internet, the only thing you need to do just to access, and you could do anything you want, One another strategy could be that you can do nothing. Basically, depending who you are, then you might get permission. But this is just to show you the extremes of different strategies. Now, with this in mind, with these lessons and with these needs, we have been working about new architecture, and I'm working with Professor Arjan here from Washington University in St. Louis. I'm helping him in this design. So I won't go in a lot of details of the architecture itself. Mostly I will talk about security of this architecture. So anyway, these are some features. The first thing we propose, and actually this is not really new, other people have proposed this, separation of addresses and IDs. So basically taking care of that problem of IP address, which is soft. So today addresses and ID are together, and the only thing we have is IP address. We are saying let us separate them. We could leave IP address as an address, but the ID should be related to the person. Okay? In this way, when you go to the internet and you authenticate yourself, now your IP address is tied to your ID, real ID, and whatever happens, it's your responsibility, like in telephone network. Okay? Other things, in our architecture, we can have multi-layer of security, and I will describe that. It's part of the design. We include all type of communication, packets, circuits, wavelengths, anything could be part of the connectivity. IDs, as I said, will be separate from addresses, and we will have hierarchy of IDs. And this hierarchy of IDs will be related to the real organization. So this is actually the real novelty of our proposal, that the hierarchy of IDs fits with the hierarchy of real organizations. Okay? In our architecture, a lot of work is delegated to servers now, both to save energy, because we might have devices which don't have energy, and also to do a lot of things regarding security, like authentication and so on. Also, services might have IDs. Again, when you ask for service, you know the ID, and you don't care where the service is located. You just ask for the service which is closest to you. And another strong point is that we separate control from data plane. Again, this is not really novel in the sense that telephone network does this and enable telephone networks to have much stronger security. Okay? So basically, as I said, in our architecture, we try to get lessons from real life, and somehow we try to mirror real life. And this is shown in this slide here. So this is a process that has been going on for several decades, merging between telecommunication and networking and computing. And now, probably in the future, this will be the situation. There are all aspects of real life here, and they will be mirrored on the internet, so-called future internet, which will include anything related to connectivity. So let us talk a little bit about addresses, as I said, and names and IDs. So basically, name is human name, ID could be a number, and this could be an address. So we would like to separate them. Today, we have, as I said, in internet, we have this strange situation where we have just one address which is used as address and as ID. As I said, we would like to separate them, and actually addresses will be related to connectivity, and IDs and names will be related to other aspects like security, routing, okay, and everything else on the internet. Our architecture is built on objects. Object could be anything: computers, routers, networks, humans. As I said, we try to include everything now in this internet. Countries, departments, processes, and they might have hierarchy and could be recursive. So basically, a set of objects could be another object. These are some details of the architecture. Each object has its profile, including security features. And actually, this is an important point that routing is based on IDs and not addresses, which will be very good for mobility. Now, separation of data and